we optimize the linear function, we can easily know the direction in which we should go by taking the gradient and moving along the gradient. But learning ratio is introduced to control basically the accuracy of our approximation. Because if we go far away from our initial point, our assumption about the linearity of the function is violated. And it means that we are starting to do it worse. We are starting to select some optimal directions for optimization. So basically, let me draw a simple picture. So suppose there is one-dimensional functions like this, and this is our w, this is our target function p of w, and suppose we want to maximize it. Basically, we can say that, okay, take a specific point, this will be our wg, we can take the gradient, we draw this basically linear approximation of this function at this point, and in a neighborhood, it's pretty accurate, yes, in this area. But then if you go here or here, we are terribly wrong about the value of the function. So this would be this blue curve would be our linear approximation of w, but we also use g because it depends on specific function. What we can do next? We can try to use not a linear approximation, but what is our next candidate? A quadratic approximation. Instead of saying that our function is close to linear function neighborhood, we can say that we can find out about the quadratic function that is close to the two function neighborhood. So we can draw it like this. This would be our quadratic approximation of our function e. It would be more accurate in the y region, and in this way we can do that. And this Newton approach says that if we have a quadratic problem, we know exact solution actually. With the function quadratic, we know exact point of the minimum. Basically, we would say that it would be the update in the following way. So if our function is quadratic, we are writing the update in this form, wg plus wg plus 1, or just vg plus 1, we obtain the optimum in one step. And you see, it's kind of a perfect speed up for quadratic optimization. We don't need many radius steps, we need only single quadratic step. And to do this, we need to include the following term in our radius step. Maybe you can remember that previously we have considered a single like this. Yes, this our function e, our current point, we take the gradient, then we multiply by learning rate, and that's all. Now we replace this alpha with this mysterious matrix alpha. There is actually a little mystery about this matrix. It's the matrix of the second derivatives of our function at the point wg. So basically, we take the matrix of second derivatives and say it's our Gaussian, we inverse this Gaussian, and we obtain a more efficient update. Can we apply this idea, this Newton method, that is theoretically faster, especially for quadratic problems, to the optimization of real networks? What was it?
We could if the minimum of that parabola lies in the area where we trust this quadratic approximation.
Yes, okay, we can do this and say, okay, now we have another alpha here. also regulate to multiply. Okay.
Mm-hmm.
Is it good now?
Still looks like we will be trapped in local minima.
More what we will be doing?
Be trapped in local minima.
Yes, but okay, we can't find a lot of It's just too hard problem to solve it like this. Or I suppose okay, we have a very little intuition of what, okay, we have some intuition, but we don't have precise statements of what function we do in the operators. Okay, so one problem, okay, actually we have two problems. The first problem, can we calculate the second derivatives using the backpropagation? The answer is yes, it's not that hard. But you can look at two problems actually of calculating this back. The first problem is this matrix is very good, or very big answer. Suppose we have a even some relatively small ResNet architecture. It has something like 10 millions of parameters. Yes, our G equals to the 10 is the power of 7. Okay, and actually it means that even calculation of the gradient is not an easy thing to do. We need a lot of compute to calculate the gradient. But for us, the things are even worse. This matrix has size d by d. Yes? So it has 10 is the power of g elements. We need to calculate. Okay, we can divide by 2 because it's symmetric. But anyway, very big number. And actually it's very hard to compute everything like this. The second one. We need not this matrix, but we need to invert this matrix to have h in the power minus 1 in this formula. It means that we need compute of the order of magnitude lenses. And it means that in this exact formulation, we can perform Newton methods. It requires too much compute, or at this part, and as well as the part when we invert this matrix. Also, I suppose that this matrix is not very good typically. When you try to invert a condition matrix, you will obtain something not very stable. Another numerical problem, we will deal with this later. So instead of the Newton methods, many people are trying to invent some approximation of the Newton method, for example, quasi-Newton methods. In this case, we estimate SR using the gradients, second gradients, second derivatives, and we have a model. One very first step we can do is this direction. Say that our h of t is close to the diagonal matrix. So all of diagonal elements are zeros, and all diagonal elements are these second derivatives. So in this case, we need to calculate the number of derivatives that equal to the dimensionality of our problem G. So it is comparable with the rest of the evaluation of the gradient. Okay, so this problem is solved, this approximation. And then, if we want to invert a diagonal matrix, we also need all of the operations. Yes, because we just take the inverse of which number of the diagonal, and voila, we have an inverse matrix, an inverse diagonal matrix. So again, it's very simple, very straightforward operation. And basically, we will be doing something similar for our narrow networks. Also, we will need another inequality. I know I need it. Yes, there I have it. Now, let's first ask, do you have any questions on this? Yes?
Please repeat one more time. How we obtain that HT approximately equals H diagonal T?
It is our assumption.
It's our assumption, and H diagonal T.
What is it?
We just say that values
speak a bit louder, please?
Okay. Yes, what is H diagonal T?
Okay. Suppose, okay, let me write it down. So we have the original matrix H, and we can say that it is a matrix of this Hij, and actually this Hij is this partial derivative, second partial derivative with respect to Wi and J, yes?
Yes.
Then we can say that for our H diagonal, Hij diagonal is Hij if I equals to J, and 0 otherwise if I doesn't equal to J. So it means that we say all of diagonal elements are zeros for this matrix. And this is way we obtain our H diagonal G. Any other questions? Okay, a question for me. Who understands what is going on? Please raise your hand. Okay, let's put some more efforts into this slide. Maybe you can ask some questions because, you saw something between, yes, you.
Okay, can you clarify this one more time? How we use this linear one to approximate the function? How we can use the linear line to find the maximum or minimum?
Okay. Let us define again some slides right. Yeah, this one. Also, suppose we have a linear function like this. And you want, for example, to maximize it and with respect to W. And if you take the derivative with respect to it, we obtain this matrix A, and this would be the direction of increasing of the specific function, yes? And it means that if we use the following updates with T plus 1, in our notation, square brackets. This one equals to V of T plus alpha A, the alpha is the learning rate, and I is the A is our derivative. In this case, we increase the function value, and by applying this operation many times, we still will be increasing the function value, yes? So for linear functions, this cases, the relation is pretty simple, and you need to take the gradients, and that's all. For quadratic function, so again, basically it's the idea of how we can optimize the system. Basically, I'm a bit sorry. Maybe I'm in confusion. Basically, we can say that for linear function, we have a linear term, a vector A.
Yes,
we can say derivative A, and
it's the gradient.
Yes. And basically, you understand that if we add, suppose some components of A are positive, some kind of components are negative. And basically, if we take the AT times T plus 1, we would obtain A transpose WT plus alpha A transpose A, yes? We just put in E of W the equation for WT plus 1. Yes?
How can we be sure that using Newton
we can prove, we can prove that we converge for a quadratic problem in one step. So what can be faster than one step? Okay, more formally. If we are working with a quadratic problem, then, okay, we can do better than one step optimization, and we reach this number of steps with the Newton methods. Yes? Okay, let me also write down it for our case. EW, W transpose W, plus maybe some other components we don't care too much. If you take, actually, when we have the matrix of second derivatives, W and Wj, it is a matrix 2A, yes, and so we would obtain that Wt plus 1 would be Wt minus 2 alpha used to alpha A minus 1. The gradient equals to A 2A. So this is the value of the gradient. This is the inverse of the Gaussian, yes? And we also have the multiplier 2 here, because of the derivative of the quadratic function. Do you agree that this is one step for Newton methods?
So basically we go from first order derivative to the second order derivative.
And we put the second order derivative outside of this gradient. So basically this is h to the power minus 1. Then we have the gradient of the e at the point Wt. So this is
even if we start from the local maximum, then we will convert.
let's see what's going on. So basically also to be more correct, I need to write down this minus here. And let's see what's going on basically with this part. We have Wt minus 1 divided by 2, A minus 1, 2 times A, Wt minus A is the inverse times B. This term equals to Wt. This term also equals to Wt. Yes? Because everything else cancels. It's a product of A inverse times A. So, after one step of the gradient or of the Newton methods, you would obtain this thing as our Wt plus 1. Actually, it doesn't depend on Wt. And also, it's pretty easy to show that it is the solution of this problem. So for the Newton method is optimal for the second for the quadratic functions, but okay, not all functions are quadratic, especially if you're talking about narrow networks. But still, we are at this stage here. We are approximating with the quadratic function. Okay, I hope your knowledge on optimization significantly improved in this lecture. Because I suppose there should be in a course on optimization, to be honest. But okay. So, we know that this updates